So let's review test 3, acid-base stoichiometry. Remember, this is eliminating the equilibrium type of problems that we'll have later in the course. We're talking about completion reactions here, and titrations are just that. So let's be crazy and start in order. We're talking about hydrogen hypochlorite, HCl, is a common disinfectant. So that's the star of our early show here. So HCl here is a common disinfectant, and it's used in public water in low concentrations, and it's also the active ingredient in Clorox. Now really, sodium hypochlorite is the active ingredient, but when it's added to water, hydrogen hypochlorite is made. That's the actual disinfectant, and that's what this reaction is about. Before, we're over here now, before the hydrogen hypochlorite is added to West Ham Beach public water supply. By the way, all public water has a disinfectant added to make sure that there isn't a bacterial outbreak. You know, diseases are caused by pathogens. Some pathogens, of course, are bacteria. So we control for that by adding disinfectants, and that's what this is anyway. All right, must verify that a safe low concentration will be added. So we're going to talk about verifying a concentration, and that's kind of what stoichiometry or acid-base titrations are. We kind of figure out what the concentration is by using a standard solution, and that's what a titration or an acid-base titration. In any case, they're saying a solution of HClO is prepared by adding sodium hypochlorite to water. So I'm asking in this question, write the net ion equation, and that should jump out at you as net ion. Net is overall. Okay, we're going to eliminate those things that aren't part of the reaction. We should know at this point we should be eliminating the spectators. And I'm telling you that the preparation of HCl, we're making HClO from these two compounds, sodium hypochlorite and water. Okay, so here's a reading skill. We're going to make HClO from these two things. So if we're going to write this reaction, we should start. Now I'm going to show you how to write a net ion reaction from this statement, and I'll get there in a second. But what I do is I'm going to start by writing what's given to me and then start breaking down what the spectators are. So they gave me sodium hypochlorite. All right. And I put that down there. And they said we have water. Those are my two starting reactants. Now, if I leave this as such, I'm already in jeopardy of getting this wrong, because sodium hypochlorite, I see a group 1 ion here, party people. Look at this, sodium. It's a group 1 ion. It's always, always, always soluble. If you have to know something, for sure you have to know who your soluble compounds are. So this is going to dissociate into Na+. It is a very good electrolyte. Things that dissociate into ions readily. Soluble salts, strong acids, strong base should never be written together in a net ion reaction. So this is going to dissociate into ClO negative, and you can't forget the charge here. Sodium is +1 in that formula, and ClO is -1 as a cluster or a polyatomic ion. Okay, water we do not break apart. I know that water can make protons or H3O pluses in the autoionization reaction, but it is not a very good electrolyte. Remember, its Kw is 1 × 10⁻14. It barely goes forward. It doesn't dissociate very well. So I'm going to get rid of this right here, and I'm going to get rid of sodium chloride. I'm going to put in these free ions. That's really important. Okay, now, so I'm going to eliminate this. I'm going to keep these ions here, and I'll fix as I go. All right, so let's continue on, and I'll just change back to my color that I was working with. At least I think so, because I'm a little bit colorblind. In any case, we're going to prepare HClO. Okay. So they're telling us we're making this. Okay. All right. Now, well, sodium ions, okay, are probably going to spectate on both sides. But before I do so, let's write the ClO negative here. And if we need to, we can write the sodium just for fun right now. Okay, but before we get started here, this is an acid-base test. There's an acid-base going on here. And what's happening is, if we're going to make HClO, as they're telling us, prepare it from these two reactants, well, the only way I can make HClO, if I'm starting with Cl negative, is that an H must be, or H plus I should say, a proton, and H plus, okay, should be donated from the H2O to the ClO negative. All right, and that of course is going to make HClO. All right, and of course, wait a minute, if the water is going to lose a proton, you should understand that we're going to make a hydroxide. They didn't say that, but it's implied that the water is going to, when it loses a proton, become the hydroxide ion. And notice something, we're also going to have that sodium that's free on one side, free on both sides, because the sodium's not going to precipitate out ever. It's a big +1 ion. Coulomb's law states that it's always going to be soluble. So we're going to get rid of that spectator ion. Okay? And some people say, they didn't say the hydroxide. How do I know I have to write the hydroxide? Well, when you're writing a net ion reaction, party people, you still have to balance the reaction, right? So if you notice, we have one chlorine, we have one chlorine here, and we have 3 oxygens, one oxygen here on the hypochlorite ion, another oxygen here, so I'm sorry, 2, and I have 2 oxygens over here. So if you don't add the hydroxide, okay, you won't be balanced. Same thing with the hydrogens. We have 2 hydrogens on the reactant side, and you've got 2 hydrogens over here. So again, all right, you'd have to add the hydroxide in order to balance this. And this gives you the idea that the hypochlorite ion is what I say an A negative, a base, right? That's what it is. It's a base. It's an A negative. Okay? And it rips an H away from water. And it's going to reform the acid called Ha. In doing so, it forms the hydroxide ion. Okay? Kind of a classic way to write this type of acid-base reaction. Okay, so that is the net ion. I got rid of the spectators, and again, there's a little bit of reading to understand that we were preparing HClO from water, but you can't forget the hydroxide here. Okay, can't forget the hydroxide, because you need that to show that it is a weak, or at least go through this reaction and figure out that, hey, I have a base here. Okay, and by the way, it's a Bronston-Lowry base. Okay, so the next part of my problem here is that I'm asking everyone to identify all the Bronston-Lowry acid and bases on both sides. Well, as I can see here, the ClO, or the hypochlorite ion, has to receive a proton from the water. You donate a proton, you are a Bronston-Lowry acid by definition. And the ClO negative ion is accepting, so you're a Bronston-Lowry base. Okay, I saw some people when I was grading these types of tests see 2 acids on one side. Acid-base chemistry works because they're going to react with each other. You can't have 2 acids and 2 bases. They won't react. Okay, that's one catch when you're doing this. Now, if you're a conjugate base on one side, okay, you become a conjugate acid on the other, right? Because a conjugate acid has 1 more hydrogen than the conjugate base because it needs it to donate it, right? Conjugate base has 1 less hydrogen. Remember, the word conjugate means same chemical plus or minus a proton. The conjugate base always has 1 less H plus or proton because it needs room to accept it. That's what bases do. Look at my arrow here. Now, water was a conjugate acid on one side. Its conjugate base pair is the hydroxide. And if we want to color code these, okay, this is one conjugate acid base pair, and this, of course, is the other. And I asked you to identify the conjugate acids and bases on both sides. All right, and that was a bunch of points there. Okay, so that was B. And some people didn't do it. Please read carefully. Okay, so moving on. The quality control chemist, Mr. G, that's me. Okay. Okay, add solid sodium hypochlorite to water to prepare solutions of HCl. So we're going to add this to water to prepare a solution to be added to the water supply. Okay, we just talked about that. So here comes some important info here. 45 milliliters of the hydrogen hypochlorite is added to a dry, clean flask, okay, and titrated with 0.025 molar barium hydroxide. Okay, so now the question is, what's going on here? It's really maybe helpful because I know when people did this test, they got things backwards. Who is the titrant and who is the analyte, party people? Well, the titrant is the substance you titrate with. The titrant is, in this case, barium hydroxide, which we should notice to be a strong base. You know, you have to know that strong bases are very soluble hydroxide salts, and group 1 ions and group 2, excluding magnesium and beryllium because they're just too small, they coulomically attract hydroxides too much that they can't dissociate completely, are your strong bases. So this is a strong base. Strong base. And you say to myself, Mr. Grodsky, is HClO, is that a strong acid? And that's a question that people had here. But what am I giving you? If you look very carefully in the problem, okay, I am giving you the Ka of the HClO is 3.5 times 10 to the negative 8. Whoa, that Ka is small. And you guys should know that an equilibrium value for an acid or any reaction is essentially the concentration of the products over the concentration of the reactants. And so if your value is small at equilibrium, you have a lot more reactants than products, which means the reaction doesn't like to go forward. It's not very spontaneous. And if this reaction doesn't like to go forward, this acid doesn't completely dissociate. It is a weak acid. Strong acids have Kas that approach infinity or undefined or just very, very large numbers because the products are favored, the proton dissociated. So this screams to me that this is a weak acid. That was one thing you had to get from that piece of data, that we have a weak acid. And weak acids do not like to dissociate, just like water above did not like to dissociate. So in a what? Net ion reaction, I keep them together. Only strong acids, strong bases, and soluble salts. And, you know, bases can be considered a soluble salt, right? Some strong bases, all strong bases, of course. Okay, so what do we have here? Well, write the net ion equation for the reaction between HClO and barium hydroxide, which we have established is a strong base. It's a soluble salt with a hydroxide. So I'm going to write HClO and keep that entire acid together. I do not write them as H plus and ClO. I did break apart the ClO before because that was sodium ClO. And anytime you've got a group 1 ion, it's soluble. And I should know that. Soluble salts, strong acids, strong bases in net ion reactions have to be written as separated ions because they completely dissociate. Only precipitates and weak acids and weak bases stick together, or compounds that do not break apart into positives and negatives like molecular compounds like water. Okay, in a large amount. In any case, that being said, so we have this. Now, what else do we have? We have the strong base. But barium hydroxide is a strong base, so it completely breaks apart into barium plus 2 and 2 hydroxides. I may need to balance, but I'm going to throw in a hydroxide. Remember, I have to balance these reactions, or these net ion reactions, but I'm going to put 1 in. If I need to add 2, I will. All right? I'm not going to write the barium. The barium dissociates, and I could put barium over here if you'd like in the beginning. And we can see if we can eliminate that. And what are we going to make? Well, this is an acid-base reaction. So the base with these lone pairs is going to highly attract and rip away this proton. This strong base is going to force this weak acid to what? Dissociate. Dissociate as much as there is hydroxide. That's a stoichiometry. So as many hydroxides are present is how much it will. Normally this acid here does not dissociate well in water. But hydroxide will force its hand. Strong base will rip that proton away. And so what do we make? Well, we're going to make the hypochlorite ion. And of course, we're going to make water. What is the product of these two things? I didn't give you the product, so you had to predict them. All right, and notice even if I put the barium here, the only way barium's going to be part of anything if it makes a what? If it makes, a precipitate with the ClO ion. And, generally speaking, low ions like this, or low charged ions, don't make precipitates. So barium, okay, is a spectator. And one rule you can help remember if you don't know your solubility rules is that the result of a strong base are ions that spectate, or ions that don't ionize water. So we're going to eliminate the barium plus 2. It came from a strong base. So it's not going to be part of the overall reaction. All right. You can think of it as a conjugate acid, maybe. I don't know. You don't have to. All right. So in any case, there we go. And that's my entire, and if you can just check for balancing, right, we have to make sure that we have the right ratios here. We have 1O. Christmas. We have 2 oxygens here. 2 oxygens. Hey, 2 oxygens. We have 2 H's. We have 2 H's, 1 Cl, and everything is balanced. Okay? So don't forget to do that. That can also be a nice little hint to figuring that out. Okay, so just clean this up. You don't need to have these arrows here. You don't need to show this, but you needed to know that was a weak acid based upon this Ka for that acid there. If you didn't get that, because I got a lot of people writing H plus the hydroxide equals water here. That is incorrect. That's only for strong acid, strong base. Okay, and titration, which this was not. And I told people that that was more of the exception. If you write that net ion reaction, you should check yourself, because most acids are weak, most bases are weak, so therefore most titrations, okay, will be weak to strong, not strong to strong here. Okay, so any case, moving on. Letter D. They're asking, well, they're saying, calculate this thing right here, this bracket. Now, this bracket, if you don't get it, is concentration. They want the molarity. The molarity of this. Okay, so how do I get there? All right, well, very quickly, they want the molarity. And that's what this titration is, right? You have a beaker, and we have a weak acid. I'm going to write it as HA. And we have a burette, or some kind of emptying device. In that emptying device, we have the strong base, the barium hydroxide, which we're going to add to the acid. That's my titrant, and that's my analyte. Okay, so if you've got that set up in your head, these problems, and I really, really encourage you to understand that the lab portion of this acid-base unit is as important as the problems. If you can connect to the lab, you really understand this. So the total of 39.7 milliliters of 0.025 barium hydroxide is required to reach the equivalence point. Gosh darn it, this is I call this a 0.4 question. 0.4. Why is it 0.4? Because they're asking for the concentration at equivalence. We are dropping a strong base into a weak acid. And we need to know, all right, what the concentration of this is. They told us, okay, that we needed this amount of the base by some kind of either indicator or pH probe. We got to the equivalence point. So the first step is to find the moles of the base that I added. And so we'll do that. And the base way to get moles through solutions is molarity times liters is volume. Get that down. So I'm going to take 0.025 molar, and I'm going to times that by the liters of the base that I added from the burette there, and that, of course, is going to be 0.0397 liters. Okay, plug this into my handy-dandy calculator, all right, and I get 9.9 times 10 negative 4. And I times 10 to the negative 4. And that, of course, is moles of barium hydroxide. But we need to match up hydroxides. So you should recognize that for every one barium hydroxide formula, there's 2 hydroxides. So I'm going to times this by 2. I saw a lot of people dividing by 2. Every one barium hydroxide has 2 hydroxides. So if you've got the moles of what? Barium hydroxide, the moles of the OH ions is going to be twice that. Remember, it's complete dissociation. It's a strong base. So I'm going to times that by 2. And when I do so, I get 0.001985. I know some sig figs here. That's moles of hydroxide ions. What's the whole point of the titration? The equivalence point. Equivalence, my friends, means that what? The hydroxides equal the protons, or in this case, the acid, the Ha. So this is the same value. So 0.001985 is also the moles of the Ha, or the acid, or the H+, however you want to think about it, the proton. Okay? They're equal at the equivalence point. You need to know that. What are we trying to find? Oh, we're trying to find the concentration, the molarity. What's molarity? Moles of the acid, that's the Ha, over the liter of its concentration. Well, we just found that right here. So we're going to do what? 0.001985 moles over the liters. And they told us way up here, we have 45 milliliters of it. Got to convert that to liters because molarity is moles over liters. So 0.045 liters. Okay? And when I do that, I get 0.044. Okay? So I get 0.44 molar. That's the answer. All right? And that'd be a 3-check question for me. Find the moles. Do the stoichiometry of the hydroxide. Notice it's equal to the hydroxides to the protons and divide by 0.045. To me, that's 3 checks. All right. Letter E. Okay. Calculate the pH at the half equivalence point. Well, the half equivalence point is half the volume necessary to halfway drive off all the weak acid. So if we know from the problem that 39.97 was needed to be added to completely neutralize the acid, well, we just need half of that. So 39.7, okay, we're divide by 2. And if we wanted to know the equivalence volume, we'd get that. But I don't want the equivalence volume. We want the pH at the half equivalence point. And so how do we do that? Well, I call this a 0.2 question. And what's 0.2? Well, 0.2 for me on a titration curve is the half equivalence point. It's half of the volume needed. But we know that at the half equivalence point, something special occurs. And at the half equivalence, there's equal amounts of what? Conjugate base and conjugate acid. So the Henderson-Hasselbalch equation, which is pH equals the pKa plus the what? Log of the concentration of the conjugate base over the concentration of the acid. Well, at the half equivalence point, where you half driven the acid to completion, you have equal amounts of these guys. And the log of 1 goes to 0. And that means pH equals the pKa. So they gave me the Ka, which was 3.5 times 10 to the negative 8. In order to get a pKa, they gave me the Ka, the pKa. Little p means negative log. So all I got to do is negative log this guy. So let's negative log that number. It's the Ka. So negative log the 3.5 times 10 to the negative 8. All right. And when I do that, I get 7.5. And that is equal to my pKa. Little p of my Ka. Very simple, but you had to know that pH equals pKa at the half equivalence. All right. So now F, we're going to sketch this titration. All right, and we're just going to do it by the equivalence, by estimating the initial pH. Well, what are we starting in the beaker? Okay, we're starting with an acid. Now, it's a weak acid, so I won't start low, but I'm going to guess you can't calculate this without an equilibrium problem. So I'm just going to give you an estimation, and anything works for me that's, below the half equivalence point. Now, we said that about 40 or 39.7 was the volume of base. So that was the equivalence point. So right around 40, okay, is your equivalence point. And I'm just drawing a whole line here that it's going to be on here. Okay, half equivalence, where we would get an important point. Now, I cannot calculate this point right here on this test because we have no equilibrium. I can't calculate the pH. We're going to estimate this pH. So just watch how I do this, okay? But I can, as we've already figured out, the pH equals the pKa at the half equivalence. So what can I do here? Well, about 40 is the equivalence, so about 20 is the half equivalence, half the base needed. And we have the 20, and we can plot this point, and it would be a point that I'm going to measure for the test, and the pH equals the pK, and we found that 7.5. So 7.5 should be your pH there, because the pH equals the pKa, right? So that's what I have there. And for those that don't see it, okay, open your eyes. No. So there it is. Okay, so here is that's about 7.5 right there. All right, cool. That's one point you can have. Now, the equivalence is going to be above this. And you should know that weak acid strong base, we're going to balloon up. Let's kind of curve this out. Let's do this. We're going to kind of balloon up because we're making a conjugate base. We're kind of flatten out a little bit, kind of keep going up, and then we're going to have an asymptote at this place here and then level off. Now, we don't know the leveling, so we'll come here, okay? But I know that, and I probably could be a little bit lower there. But again, it's all estimation here. Probably more flattening out here. It's going to go up a little bit, and then it's going to rocket up at the equivalence, and then be some sort of an asymptote. Okay, and they said stop at equivalence, and I'm just going to say that the equivalence point is going to be above 7 somewhere. So I'll say here. And I can redraw that once I know my final pH. Okay, but I know that I'm on the asymptote at 40. So I'm going to get I gave a check out if you had the direction correct. If you're going low to high, that was one check. I gave you a check for the correct point here for 20 and the pH. I gave you a correct check to know that your equivalence volume is at 40. I can't measure the pH, but I also give you a fourth check if your equivalence volume is above 7. Okay, so that's how I did that, if you want to try to understand what happened there. All right, let's continue on. In your sketch, explain why your equivalence point was below, above, or at a pH of 7. All right, well, it was above. That's one check. Justify your answer. Well, what was my reactions? Go back to your reaction, okay? So we were dropping what? Hydroxides onto HClO. Does this look familiar? That's the reaction in the titration. And so we were driving this reaction to completion to ClO negative and water. And you should recognize that this reaction goes to completion at the equivalence point. At the equivalence point, we have what? Annihilated all the acid in the beaker, and we added just enough of OH minus. Okay, but we've made all of the acid become the conjugate base. So really, to explain this, since all of the acid has become the conjugate base, and now it's just sitting in water, the water is the most prevalent species, what is this conjugate base going to do? Well, it's got lone pairs. It's going to a little bit, it's an equilibrium reaction. You don't have to know that, but it's going to take some H's away. So it's going to rip some H protons away from water. It's acting as a base. It's a conjugate base, right? And so what it's going to do is it's going to reform the acid. That's why it is a weak acid. But more importantly, it produces a hydroxide. So what you could say, the reaction works perfectly. You could say that at equivalence, all of the conjugate what? Remember, at equivalence, all of the strong base, the hydroxide ions, did what? Forced the weak acid to give up all of its what? Protons. And we made 100% HClO and water. There's no hydroxide left, and there's no acid left. Everything was converted 100% to HClO. For my people, I make my people know that this point here, there's 100% A negative and 0% HA, theoretically. And at this point, it's 50%. And the reason I make you write that is because so you can see that A negative and HA. In the beaker before we started, we had 0% theoretically A negative and 100% HA. Okay? So knowing that we forced it all to become the what? The conjugate base. Well, the conjugate basing in water is going to go forward a little bit based on its Kb, but it's going to make some hydroxides. And of course, these hydroxides will do what? Increase the pH. It's not good enough to say the pH increases because I added base. All of the conjugate base that's been formed at equivalence does react with water, and it ionizes water into the hydroxide ion, which will, of course, raise the pH. Okay, very important. Some people said, well, you had some base, and you got too vague. The best is understanding this. Okay, B, or H, I should say. Calculate the final pH. This is a 0.5 question. When we did our titration curves and predicted, this is a 0.5. So how do we do this? Okay, if 50 mils of the titrant was added, titrant, of course, is the base. Well, we see equivalence. Equivalence is essentially at 40. Now, I gave you 39.7, and we stopped at 50. So if we do our math here, that's a 3, this is 4.9. Sorry if this isn't New York State math anymore. I get 10.3 milliliters of extra. So from this point here, we have added extra, okay? What? Hydroxides. Right? We neutralized it at 39.7, so we've added extra beyond the equivalence. So at this point, there's no more acid to neutralize the OH minus, so we have extra hydroxides. So how much hydroxides are sitting in this beaker here? Remember, it started at 45, and then we added, don't forget, the x-axis here is how much titrant added. You have to add 50 milliliters. So the goal here is to get the concentration of the hydroxide. Negative log it, get the POH, then subtract it from 14. So I'm starting with 10.3 milliliters. We're going to convert that to liters, so 0.0103 liters. I'm going to times that by the concentration of my base, which was 0.025. Okay, and that's molarity. For the millionth time, molarity times liter, okay, gives you that. So molarity times my liters there, and so I get, I think, let me just make sure I get that. So let's put this in my handy calculator, and I get 0.0103 times 0.025, and I get 2.575 times 10 to the negative 4, and that's moles of what? Barium hydroxide. We need hydroxides. So the ratio is for every 1 barium hydroxide, there's 2 hydroxides. So this number we times by 2. And you get 5.15 times 10 to the negative 4 moles of hydroxide. If you want to put it up and cancel units and do that, but hey, let's just get to understanding it. And what am I after? I'm after molarity. Well, molarity is moles over what? Okay, moles over liters. What's the liter of the solution? Don't forget, you've got a little beaker. We had 45, we added 50. Now 50 plus 45, okay, is 95 milliliters. Got to go to liters. So 0.095 liters. So I'm going to divide that by 0.095 liters. And my molarity, or my concentration of my hydroxide, is equal to 0.00542. Hey, that is great. Let's go find a pOH. So that's negative log it. So negative log, put it into an exponent. I get 2.27, and I'm going to subtract from 14 to get the pH. Okay, and I get 11.7. So the pH is equal to 11.7. And I'm going to plot that here, 11.7. Here's 11.7. So my final pH is something like this. And my asymptote kind of levels off here. All right, I probably could do this curve a little more justice here. Okay, and was I green here? So I'm going to come up here, and then yeah, something like that. And this, again, this point is estimated here. All right, good enough. Any case, I asked you to circle your addition to the sketch by leveling off. And there's a check there. Okay. Letter J, which of the following indicators would be best choice to determine the endpoint? Well, because my pH is above 7, I want to pick the pKa of the indicator that's closest to the equivalence. Now, I know it's above 7, and we're estimating. Notice I gave you only one above 7, okay, since we can't calculate that pH yet. So you would tell me it's thymophalline, and you'd get credit for that. But I said justify your answer, and all I would have to say here is that it's the only indicator that its pKa is closest to the what? Equivalence pH. You can say it's on the asymptote. Okay, it's on the asymptote. The pKa is on the asymptote. So the pK of 10, okay, would be right around here, and it's on this kind of tangent line. Okay, and that's important. So you could also tell me that it's on the asymptote, that the pKa is on that kind of tangent line that goes up here, that exponential. Okay, so if the pKa, and another nice thing too is you can say that the most appropriate indicator is where a pKa is plus or minus 2 away from the equivalence pH. Again, we can't calculate the equivalence pH, but you had to know that it was above 7 for this test, and the only one above 7 is thymophalline. But the best answer is to say that its pK was closest to the equivalence pH, okay, or it's on the asymptote. Now, K, explain why using an appropriate indicator would eliminate the need for a pH probe. Well, what was the whole point of this titration? The whole point of the titration was to do what? Verify the concentration, to find the concentration of the weak acid. That's it. Okay, that's all we were trying to do here. So, an appropriate indicator would help us get that what? Concentration. What do we need? We need the appropriate indicator to give us an accurate endpoint which stops the titration. Okay, endpoint, which is a color change. You stop the titration when that color change occurs, if you have an appropriate indicator that we just picked. Because it what? Because the volume, so important to understand, it's the volume of titrant, in this case the strong base, accurately what? Accurately approximates the equivalence volume. We're all after the volume. Take a look at our curve. Okay, now if we didn't know how much of the base, if we had this curve, we would know here it's 40. Now in this problem they told us. Okay, but most titrations you have to keep adding until you get and stop the what? You stop the titration. Now it's important you understand this. If I stop the titration on this little green out portion, and I'll draw it in a different color here. If I stop the titration here, okay, because I'm on this straight line, the volume I would get is essentially the same at equivalence. Because we're on this asymptote, being here or at equivalence does not change significantly the volume that we would need to answer this question. And of course, that's the key here. All right, so accurate endpoint. Appropriate indicator gives us an accurate endpoint, and the endpoint is not the same as the equivalence volume. So the endpoint, okay, approximates the equivalence volume using the volume of what? The base that we added times its molarity. We get the what? Moles of the hydroxide, which equals at equivalence the moles of the H+, which we can divide by its original concentration, its original volume in the beaker to get the concentration of the acid. That's how we were doing this. So you needed to talk about that the endpoint on the asymptote or is a great approximation of the equivalent volume. You can't say that the indicator gets us the equivalence point. It doesn't. It's very close, but it approximates. I needed to understand that endpoint and equivalence point are not the same. The endpoint is a what? Approximation. Okay. So letter L, all right, is a 0.3 question. All I was asking for you was to draw, okay, the chemical species except water in all appropriate ratios. I probably should have said, conjugate acid base, but I wanted to see what you put here, okay? So I don't know if my key is perfectly correct, but what's left? What do we have if we stop the titration at 22? So let's go back, not knowing what this is, going back to your curve, okay? This would be 0.3 on my curves. I mean, again, for people that are jumping into my presentation and saying, wait a minute, I'm learning, but you're saying things that we didn't learn. I call the initial concentration 0.1 of a curve. I call a halfway equivalence 2. I call the equivalence 4, we're estimating in this test, and the final 5. Anywhere in this buffer position is just before what? The initial concentration, and just under the what? Yes, I'm still at school. Okay. Is your buffer position. And now I said you can calculate this buffer position using Henderson-Hasselbalch. And I'm telling you it's at 22. This is 22. What is this pH? Well, a couple of things you should recognize is if I am 50% conjugate base and 50% conjugate acid at this point, if I keep adding hydroxides, my conjugate base value will be higher. Okay? And all I want you to understand is that I should see more conjugate what? What are we driving as we keep going? We're making more of this ClO as we get closer to equivalence. We get to equivalence, it's 100% ClO. So I needed to see that ClO negative, okay, was in greater concentration than what? The conjugate acid. There's still some conjugate acid there, okay? And you're in a buffer scenario because you have a conjugate acid-base pair. When you're at point 21 or any point on this buffer region, buffers means conjugate acid-base pairs, okay? When you're on this region, you have both available, okay? And as we get past the 50-50, get closer to equivalence, we're going to have less acid and more conjugate base. And that's really all you needed to draw that. What I did not want to see, so you got a check if you drew ClLO and you drew HClO, H, the conjugate acid, HClO, and you had the ClO negative greater than the HClO, and you could not have any hydroxides in here. That is a limiting reagent, okay? And for those that didn't see it, what do we know about Henderson-Hasselbalch? pH equals the pKa plus the log of the conjugate acid, A minus in this case, is this, over the concentration of the what? The acid, the Ha. The Ha, or the weak acid, is this guy right here. And so if you're above half equivalence, as you can see from the graph, this is going to be a little bit higher. How much higher is it? It's going to be higher than 7.5. Oh, 7.5 is your what? Oh, that's your pKa. So what's the pH? We're going to have this what? 7.5. We determined that was the pKa. Now, wait a minute. We should see that from this curve that we're going to rise up until we hit this kind of, exponential rise here. This should be a little bit higher. The pH is going to be higher if we're adding a base to a weak acid because we're making hydroxides. So this expression here has to get bigger. And that means you're going to have more what? Conjugate base. So when you have more A negative over HA, this expression goes to be a positive expression. And you have to add that, whatever that number is, and you can actually calculate that, okay, by doing a Stoich reaction, or I say a Stoich table, okay. And I'm not going to do that here, but I did that in the key. So I actually figured out the moles of each, and then showed you that ClO0 had to be bigger. I don't think I need to say that. If we were in front of the half equivalence point in a weak acid strong base titration like here, my pH here is lower. Why? Well, because I haven't added enough what? Base to get to halfway. And if my pH is lower, this expression would have to be a negative. The only way you get a negative if you have what? If you have greater amount, if your what? If your reactant here, or your denominator, is bigger. That would make this number in this box a number less than 1, and a log of less than 1 becomes a negative number, whatever that might be, and you'd be subtracting to go down. Okay, so that's really what that point 3 question was about. I didn't need the barium, but I cannot see what? Hydroxides. Okay, you should understand that in the point 22 here, we had a lot more HA left in the beaker. Right? Because if you want to think about it, it's 0.002. I didn't read that carefully. So that's 0.002. And we're going to do, well, who is smaller? Well, this is minus 0.0011. That goes to 0. This is plus 0.0011. Of course, that goes to 0011. That plus 0 is that. We're going to minus 0.0011. We get 0.009. And you can clearly see, party people, who is the largest value. Okay, and you can see that there should be greater amount of ClO0. All right, so there is a greater amount of ClO0 at the end of the reaction. Remember, this is a completion reaction. These are moles in this table. Then there is HClO. You can actually put this into the Henderson-Hasselbalch and verify the pH here if you'd like. But that's why there is a greater amount of conjugate base, okay, in my drawing. If you wanted to add the bariums, you could, but I should not see any hydroxides. All right, I hope that helped.